feel like I'm telling you this for the first time.
No.
You've not seen this before?
Yeah.
It goes through a stepwise cyclic process where the energy captured in that from that photon of light is converted into NADH and NADPH and ATP, ultimately. So then but it has to do with capturing energy in this region of the spectrum. If we go to the infrared, and we'll stop here in terms of our discussion with respect to spectrum, infrared radiation causes bond vibration. Okay, and again, bond vibration, the frequency or energy that's required to cause a bond to vibrate depends on how strong the bond is. Stronger bonds require higher energy radiation, weaker bonds lower energy. So as we scan a range, we can diagnose what kinds of bonds are present. That's the basic premise here. The IR region, again, instead of doing either lambda or frequency directly, this is what we look at in the infrared spectrum. It looks something like this. You get a chart, and on the y-axis here will be percent transmission. This is the percent of the light that actually passes through the sample. And so it'll be labeled like 100 up here and 0 down here. And on this axis is 1 over the wavelength in centimeters. And the numbers down here are called wave numbers. And according to the slide here, they range from about 2.5 to 25 times 10 to the, at any rate, this ends up being about 4,000, and this is about 400. And those are centimeters minus 1. Like that. Now, this takes a little bit of inversion and upside down thinking and so forth. Which end of the infrared spectrum here is the high energy end?
It'll be the low energy inversion.
Remember, since we're upside down, remember, long wavelengths, low energy. Short wavelengths, high energy. So as these numbers start to become smaller, the reciprocal becomes larger. And so the high energy end of the infrared spectrum is up here, low energy end down here. And just a couple of breakdown points. Beginning about 1400 or 1500, we cross over into a diagnostic area, and down here is called the fingerprint region. So that kind of goes between 1500 and the end of the spectrum. We usually don't analyze this spectrum. It's where real simple bonds are vibrating, like carbon-carbon single bonds, and carbon-oxygen single bonds, and a number of others. And usually this portion of the spectrum is complex. More complex than we can analyze, particularly for larger molecules, and so we don't tend to pick it apart like we do the diagnostic region, which is up here above 1500. And so what we do is we treat it like a fingerprint. Let's say that I'm working with a chemical and I say, I think I've got 5 hexanol. No such thing, that would be 2 hexanol. Let's suppose I have 2 hexanol. And that I'll look at the spectrum and I'll be able to diagnose the presence of the alcohol, but all that stuff in the fingerprint region is too complex for me to actually analyze. So then what I'll do is I'll get the actual spectrum for 2-hexanol and I'll compare it side by side with mine. And in that fingerprint region there ought to be a peak-for-peak correspondence. Otherwise I haven't identified it. And I can eliminate that compound as a possibility if the fingerprint region does not match. Does that make sense? Now, since there's zillions of organic compounds, you don't want to identify a compound by comparing every possibility under the sun. You want to do this a little bit more intelligently by narrowing it down with other tests first. But different regions of the spectrum, this is essentially a diagnostic region, have different purposes. And the separating point is at about 1500, maybe 1400, depending on the author of the textbook you're reading. We can think of a bond vibrating, an analogy for the bond vibrating, if we can think of a couple of balls connected by a spring. And we can think of them being either compressed or stretched vibrating back and forth between these two states, and that the average value would be an equilibrium point. Does that make sense? Some characteristic frequencies and energies. Here we've got carbon-hydrogen, carbon-deuterium, and carbon-carbon bonds. What's deuterium?
Heavy hydrogen.
Heavy hydrogen. And it turns out that we see that the mass of the vibrating atoms makes a difference. Notice that we see, in terms of the wave numbers, that's what we're talking about here, we see carbon-hydrogen stretching at about 3,000 reciprocal centimeters, out about right in here, whereas we see carbon-deuterium at 2,100. So that would be down here somewhere. That, in general, as the masses get larger, the wave numbers get smaller, the energy gets smaller. Look at carbon-carbon, down around 1,200, down in the fingerprint region. Okay, carbon-carbon single bonds at 1,200, carbon-carbon double bonds, stronger bond, more energy, higher frequency, higher wave numbers. By the way, the wave numbers are directly proportional to frequency. That makes sense, doesn't it? Okay, and finally, a carbon-carbon triple bond is in a region where we hardly see anything else. So if it's there, it's diagnostic for either a carbon-carbon triple bond or a carbon-nitrogen triple bond. You can see that. Carbon-nitrogen triple bond and carbon-carbon triple bond are right at the same place. We go through different possibilities here, and there are elaborate tables available for you, so when you've got an infrared spectrum, you can see what you have in terms of bonds. I'm just looking at the different possibilities. Is this making some sense?
Wait, just look at the hydrogen, the deuterium, and the carbon up there, the single bonded ones.
Yeah.
So you're saying a carbon-hydrogen requires more energy to vibrate it than a carbon-deuterium, right?
Right.
So the
It's like
a lighter one requires more energy?
Yeah, it would be, for example, and if you did this as a physics experiment and you use billiard balls connected with a spring and you cause them to vibrate, okay? And best to do it vertically, so you hold one and let the other one vibrate. Then if you took cannonballs, much heavier, but use the same spring, how would that vibrational pattern look?
Be longer.
It would be slower.
Would be
Does
longer.
that make sense? In other words, the frequency goes down with the heavier particles. That's what that says. Interestingly, the spring is the same, so the bond energy is the same, but because of the difference in the masses, the frequency of vibration changes.
Okay. Yeah.
Because we have the same bond energy between carbon and hydrogen and carbon and deuterium, because this is an isotope of that. We recognize deuterium is heavy hydrogen. It's got, instead of just being a proton in its nucleus, it's what? A proton and a neutron. And because it's twice as heavy, its frequency is much shorter, or much longer. If not longer, but it has a fewer cycles per second. This vibration. All right? Now, interestingly enough, the treatment in infrared by experts is really powerful. Those people that do this a lot can identify a compound by the infrared alone. I'm not in that select group. Nor will I expect you to become part of that select group. Generally, what most of us do as organic chemists is learn enough IR to narrow down a set of possibilities to a few candidates. And the infrared is capable of doing that for you. When we couple that technique with the technique described in Chapter 13, NMR, you can identify a compound directly from those two techniques together. Okay? Let's maybe do one or two more slides here. It turns out that there's more than just simple single balls vibration modes. If I start making multi-atom molecules, in this case we're looking at water, there are actually 3 modes of vibration for a water molecule. If I'm the oxygen atom and my fists are the hydrogen atoms, there's a symmetrical vibration, like that. where the hydrogens are vibrating in sync with one another. And then there's an asymmetrical stretch that looks like that. Different energy, different intensity in the spectrum. And then there's a scissoring vibrational mode as well. Okay, that's bending as it's described here. And it turns out that depending on how many atoms we have, N atoms will give us 3N minus 6 vibration modes in the infrared. So what does that say about larger molecules?
Massive vibration.
Lots of vibrational bands that you'll see in the spectrum. And that's why with larger molecules, the fingerprint region becomes overly complex. Only at the diagnostic region remains fairly clear in terms of special bond characteristics that we can identify. In the fingerprint region, usually we just compare band for band with a known standard. How are you doing? So if I had a 6-atom molecule, actually let's figure out how many vibrational modes would be in ethanol, as we just talked about. Alcohols, we've got C2H6O. So I've got how many atoms? 9. So 9 times 3 minus 6. Oh, 21. Who said 21?
John.
21 separate bands could appear in the infrared spectrum. Now they won't all. Not all of them will appear. I don't want to get too much further today. This is a discussion of the fingerprint region. And they're defining it as between 600 and 1400. The region at about 1600, 1500, 1600 and higher is diagnostic for certain fingerprint or certain functional groups. I'll stop at this slide. Did I promise to stop at this slide?
I don't think it was a promise. You're all right.
Perhaps a misleading hint. Okay. It turns out that bands will only show in the infrared if there's some polarity associated with them. Imagine yourself as being a bond and a cycling electromagnetic radiation passes by. One moment it's cycling in the positive phase, and the next moment it's cycling in the negative phase. You will cycle in sync with that light, or you'll start vibrating if the energy is just right and if there's enough polarity for you to do it. In other words, the bond itself has to have a positive pole and a negative pole in order for it to be excited by a cycling electrical field. You understand what I'm saying? And so there needs to be a little bit of polarity there. So here's the electrical field oscillating. Here we're in the compressed mode, here we're in the expanded mode. The bond itself needs to have some charge separation in order to be excited by that cycling. If the bond is perfectly nonpolar, it's not going to show in the infrared. Okay, so what kinds of things would be perfectly nonpolar?
Carbon-carbon.
Yeah, carbon-carbon bonds, which we expect to be very common in organic molecules, particularly in nonpolar molecules in the middle. So if I've got like an octane, the bond between, or a nonane, the bonds between carbons 4 and 5 are going to be pretty much nonpolar. And we're not likely to see those particular bonds appear in the spectrum. So this 3n plus 6, or minus 6 formula tells us the number of possible bands. The real number of bands depends on polarity as well. Okay? All right, we'll call this a day. So I hate to let you go.